Hello, yeah, I'm back for the second part of the 2015 Oxford PAT. It's a slightly different format this year, although we've still got section A and section B for the maths and then the physics. The physics questions don't have any obvious dividing lines in them. They've just got a whole load of questions. It's not like we've got multiple choice, then written answers, and then long questions like we've had before. I'm still going to split them up into multiple videos because I don't want to do some massive, hour-long video or something like that. So let's see how we get on, and I'll chop them up into bits as seems appropriate. Right, let's start off here. We got a ball thrown at an angle of 30 degrees up from the horizontal. 30 degrees, speed of 10 meters per second, off of the top of a cliff, which is 10 meters above a flat beach. How long does it take for the ball to hit the beach below? Use G to be 10 and air resistance neglected. Right, as much as SUVAT is overused, these are the ones where, well, it is actually useful. If we're trying to get a time when they're giving us a velocity, we're in that middle bit. There's the velocity ones that make it worthwhile for using SUVAT. So let's take positive as down. So we got 10 meters down. We're going 10 sine 30 upwards, so -5 at the beginning. We don't care about V. A is 10 down, and then T is what we're trying to find. So we're going to use S equals UT plus a half AT squared to get that 10 is -5T plus 5T squared. So let's get rid of all the 5's. T squared minus T minus 2 equals 0. T minus 2T plus 1 is 0, so T is equal to 2 seconds because we don't want to go 1 second into the past to see where it would have come from. So a nice easy starter. Question 12, an ice cube slides down a frictionless slope at angle alpha to the horizontal. Right, so alpha, ice cube heading down the slope, sits on a horizontal table height h above the ground. That's a capital H. If the ice cube is released from rest at height little h above the ground, okay, where was I? What is the speed of the cube when it's halfway down the slope? So we want to do conservation of energy because we're getting our GPE going to kinetic energy. So our half mv squared is going to be mg, what's our h? We're halfway down the slope, so it's going to be a half of little h minus big H. So get rid of the halves and the m's and square root. So v is the square root of g times little h minus big H. So another really quick one. Now we've got question 13. Using your knowledge of solar eclipses, estimate the radius of the moon. You may assume the radius of the sun, distance from Earth to the sun, distance from Earth to the moon. Right, so they're setting us up for similar triangles here. So if we do the big triangle, because of course if you've got the Earth over here and the sun over here, all of this, then the moon's just getting in the way. It's the same triangle, give or take. I mean, you can get little variations, but more or less it looks about the same size. So we just need to compare these. So what have we got? We've got that the big distance is, well, let's do it all in thousands of kilometers. So that's 150,000. We've got that is 700,000 kilometers. That's 400,000 kilometers. So to put this into, we want 10 to the 3 kilometers is our units on all of this. And we want to say that, which way we want to put the radii at the top to make it a little bit quicker on manipulating everything. So we want r divided by 400. So let's get rid of a whole load of zeros. 1, 2, 1, 2, 1, 2, 1, 2. So r is going to be equal to 28 over 15 times 10 to the 3 kilometers. But if we wanted to make that a little bit more, I don't know if I want to make that a little bit more palatable really, but if I did, we'd be saying that, what's that going to be? Well, let's borrow one of these 10s and make that a 280. So 20 15s is 300. So that's going to be 18 takes us to 270. So 18 2/3 times 100 kilometers, whatever way you want to put it. But I think we would have been fine just leaving it like this, really. They haven't asked for a format, and they're still keeping us off the calculators, quite rightly. So they can get whatever they are left with. Write an expression relating the angle of incidence θ1 and the angle of refraction θ2 of a ray of light travelling from one optically transparent material with index refraction m1 to another with m2. Sketch a diagram of the ray of light, clearly labelling the angles and indices of refraction. And then when do we get total internal reflection? Right, okay, so we've got this set up here. So let's make that N2, let's make that N1. Let's come up here. Let's move away from the normal. We can put, so that would be saying that N2 is less than N1 because we moved away from the normal. That would be our θ2. That would be our θ1. And we can say that N1 sine θ1 equals N2 sine θ2. So if we've got so θc is going to be when, θ1 equals θc when θ2 equals 90 degrees. So therefore we're going to say that N1 sine θc is equal to N2. So sine θc is equal to N2 over M1. That's just getting our critical angle. And then we can say that if θ1 is greater than θc, then we've got total internal reflection. And that's where θc is sine to the -1 N2 over M1. So that's just straight out of your physics textbook, really. Fairly straightforward stuff for 3 marks there. Quite a lot to write, but fairly straightforward. Question 15. Consider a mass and 3 strings all lying on a horizontal table. So we don't have mass in play then. Or weight, I should say. We've got mass, but we don't have weight in play. The strings exert forces outwards on the mass as shown below. The mass does not move. What is the force on string C in terms of the force on string A? So, well, let's resolve then in the left-right direction, because then it takes B out of the equation. So we'll have that A is equal to C cos 45 degrees. So C is going to be equal to the √2 multiplied by A. So that's fine. What's the relationship between the force exerted by string A and the force exerted by string B? So, well, if we resolve that way, or by symmetry, I suppose is another way of putting it, because A and B must be the same. They've got to be. Well, actually, you can see even more if you resolve this way. So let's get rid of that. That's actually mean, yeah, let's do resolving that way, take C out of the equation. So we're going to get that A cos 45 is equal to B cos 45. So A has got to be equal to B. Thing is that, yeah, because all this is symmetrical about this line. That's the thing. I mean, there's no way we can distinguish A from B if this isn't moving. So they must end up being the same. So bisymmetry is another one of those powerful things that we can use on that. This is going swimmingly so far. A non-rotating ball of mass 2 kilograms slides on a smooth, frictionless horizontal surface at speed of 1 meter per second. Collides elastically and head-on with a stationary ball, mass 1 kilogram. Right, okay, so we've got 2 kilograms going at 1 meter per second. Then we've got a 1 kilogram which isn't moving, 0 meters per second. What are the speeds of the two balls after the collision? Right, so we've got we need to do conservation of momentum and conservation of energy on this, because it's elastic, so we can do conservation of energy. So let's say we got U and V. So we can say conservation of momentum. We're going to get that 2 is equal to 2U plus V. And then we can say conservation of energy. I suppose some people might do this with a coefficient of restitution stuff, but a lot of people haven't done that. Yeah, because this is going to be a half mv squared. So that's a half of 2 times 1 is 1. A half mu squared. So a half m again is 1 times u squared. So that's why we just got u squared. Is a half mv squared. So that's going to be a half of m is m times v squared. So we've got these. Now we just need to, well, let's get rid of v maybe. So we've got 1 equals u squared plus a half of 2 minus 2u squared. So we can take the, well, let's take the 2 outside. Let's make that a u squared plus 2, because we've got to square it, 1 minus u squared. 1 equals u squared plus, what we got here, 2 u squared plus 1 minus 2u. Right, I seem to be taking more time over this than I should be. So what have we got? We've got a u squared plus 2u squared, so we've got 3u squared. We've got a minus 4u, and then we've got a 2 minus a 1. So we've got that is equal to 0. Is that going to factorize on all of this? Let's just come up here. I'm sure it will do. So let's assume that it will, because otherwise they wouldn't have given it to us. So it must both be minus. So we've got u equals a third or 1. So, well, if u equals 1, well, actually, let's do it work out. If u equals 1, then we've got to have v 0. It's like they've missed each other, so it ain't going to be that one. So what have we got for u is 3. We've got 2 minus 2/3, so we've got 4 over 3. So we've got, yeah, u equals a third meters per second, v equals 4/3 meters per second. I feel as though I took too long doing all of that for 4 marks. I mean, it was straightforwards, but I don't know, maybe I've just done more maths than I needed to there. Right, is that going to be a good place to stop? I've done 5 questions or 6 questions or whatever it is. So I think I will leave this video here. And then, because they're bound to get more difficult as we go on, then I'll come back and do the next batch in subsequent video.